So for this video, we'll be discussing programmable logic controllers. So here's the overview of this lecture. So we'll have a brief introduction and history of programmable logic controllers or PLCs. What are the advantages that led to us using it more over the traditional control methods? And then what is the actual structure of a PLC? And then what are the inputs and outputs that it receives? And then how do we program it so that we can use it for our industrial applications? And some examples on how to program or interpret our control setup and interpret it as a program that can be loaded into our PLC. So again, a PLC or a programmable logic controller is a solid state digital computer or controller. So I use the word computer because it is still technically a computer and it is solid state. That means it is based on semiconductor electronics. So that means it has transistors, diodes inside its circuitry of the PLC. So it is specifically intended for automating industrial processes. That means it has been ruggedized and adapted for control of manufacturing processes such as assembly lines or robotic devices. So as a computer, the PLC also performs logic operations, sequencing, timing, and counting and mathematical calculations. Well, basic mathematical calculations. So here's an example of a PLC. So we have a PLC, and then we can connect to it. We can interface to it inputs. So you have photosensors, or the inputs could also just be manual push buttons, which can be operated by your operator. And then it can also send outputs that can drive actuators such as pumps, motors, and then also lighting. So before PLCs, most of the industrial control tasks were typically implemented using a hardwired relay logic. So for example, this is the circuit um, that you want to implement. So you actually have to implement each individual of these relays and contacts and active and coils that control your say motor. So you have to hardwire all of them. So that means technicians or electricians would again wire the system components based on this circuit diagram that is developed by, say, an engineer. But if there was an error, then we have to replace individually or most of these components if there was an error. So that would also mean that if there was a change in function or if we want to update our operation, then we also need to rewire the entire system completely. And one of the main drawbacks of relay systems is that arcing can happen. The charges from one end of the contact to the other end of the contact can actually break the air resistance, and cause for charges to actually flow from the contacts, even though they are intended to be open. So when that happens, high temperatures are generated, which can actually eventually weld the contacts shut, and obviously that can damage our system. So in the 1960s, PLCs were introduced by inventor Richard Morley to provide the same functions as the relay logic systems that we had, but allows for a more flexible and modular approach. So it was quickly adopted by the industry by the 1980s, and it was the popular option for industrial automation and control. And also, the steady decline in cost and increase in functionality continued to make PLCs very popular. So what are actually the advantages of PLCs? So again, um, it is can be implemented flexibly compared to the hardware systems. So again, you don't need to wire the devices or the real relay contacts. Instead, you actually do this through programming the PLC. And then also whenever you want to change or update your operation, so you don't need to rewire the relay system. Instead, you just change it on the PLC program or take your PLC program and then upload that to the PLC. Also, PLCs provide for a compact and modular design. So that means you can easily add, remove, or replace the modules of the PLC. So that also means that you can actually easily expand it. So for example, the PLC is usually has, say for example, initially has 20 inputs and like 10 outputs, but the actual controller of the PLC can actually manage a higher number of inputs and outputs to that. So what you could do is just buy an additional input and output modules so that you can actually take advantage of the capacity of your PLC. So yeah, and then it is also cost effective because again, updates or expansions does not require new components. So when you try to update your system, you don't need to replace the components themselves. What you do is just update the program and then download it to the PLC controller, and then that's it. So your system is updated. And again, it is reliable because it uses solid state components, which has a much more longer operating life. And also, most PLCs are robust and can survive harsh conditions, which includes again severe heat, cold, dust, and extreme moisture. However, the PLC also has some disadvantages. It cannot perform or handle complex data. When we want to handle complex data, so we actually have our regular digital computers, which is for example your PC or laptop, for that, for those specific purpose. So here's actually a table that compares your regular digital computer, so your general purpose computer such as the PC, laptop, or your MacBook, and then the PLC. So again, the PLC is specifically designed for automation and control, while our everyday computers are designed as a general purpose device. So we can practically do anything with our digital computer, with our personal computers. While for the PLC, again, it is specifically designed for industrial purposes, primarily automating and controlling industrial processes. And so also since it is optimized for industrial control, so it does not really have storage or display options. But newer PLCs may have some storage, may actually have some computer attached to them that allows for you to calculate and display and store massive amounts of information. But again, that is already the digital computer that is attached to the PLC, but not the PLC itself. And also, when we want to create a program for the PLC, so you don't really need computer programming knowledge. So you only need to have an understanding of logic functions. And one of the main differences as well is actually the PLCs run instructions parallel. So when you put the program there, the PLC actually scans all of the code and then it will actually run it parallel. While most computers now, most general purpose computers are designed to run operations sequentially. Although you might not be familiar with this one, but for computer engineers, they might be, or computer scientists, they might be familiar with this. But you have just to remember that the tasks or the operations are performed in parallel by the PLC. And also, again, well, this is counted as an advantage. Well, PLCs are robust, and then again, it is well suited for harsh industrial environments, while your regular general purpose digital computer or personal computer are not suitable for this harsh environment. So the PLC is composed primarily of these five components. So you have the input modules. So that's where you interface your input. So it could be digital inputs such as push buttons. It could be relay contacts or limit switches, or you could also attach analog inputs such as sensors. So you can actually send analog information, and then there will be an analog input interface for through the input module. And then you have the processor that receives all of those inputs and then runs the program that is set or developed by the programmer or the engineer using a programming device. So you have a programming device. It is usually an external console or a computer itself. It could be a general purpose computer like a laptop or a PC, and then you just attach it to the PLC while you program it, or you send the program to it and then you detach it, so you could run your processes later on. And then the outputs will then be sent out to the output modules, which is quite similar looking to the input modules. So it's just going to be an interface where you can send out digital outputs or analog outputs. So the digital outputs could be a switch that enables motors, or an energizing input that enables solenoids. So those are digital outputs, but it could also be analog outputs where you send out varying voltage or varying current to control certain parameters. And then the operator interface. So it's simply just an interface, or the human machine interface that exists in a processor that is aside from the programming device. So the programming device is technically also an interface for us humans, but is primarily designed for the programmers. So and it's only used when we program or when we send or when we update program or the processes that we want to run on our processor of our PLC. So while it runs, so the operator interface has it could be in the form of LED displays, or it could actually be an actual touch screen that gives out information. So, or it could also be some push buttons in the operator interface that you could actually attach into the input module as part of our inputs, or it could be an override start and stop button that is in the operator interface. So, yeah. So these are just some of the popular brands of PLCs. So here's an example of an Omron CP1E PLC. So you can see that it has 20 input and output lines, and this Omron CP1 can actually be expanded. So this same controller can be expanded with additional input output lines for up to 140. So, but for this basic module, so you have 8 relay outputs. So you can see here that it has 8 relay outputs. You can see it's 0 to 07. Those are the relay outputs, and then it has 12 analog inputs. So you have here 00 until 11. So those are the 12 analog inputs. But you can also see that it has some other input lines, which is for the power and for some push buttons. The COM, I believe, is the ground or a common. Yeah, the common or the ground. But there's also a separate ground here for the power source. Okay, and then it uses ladder logic, which we will discuss later. So it uses ladder logic in programming, and we can program this using a PC uh, through a USB connection. So there is I believe this says that this is peripheral, so you can open this, and then you can see a USB connection there. So inside our processor, the processor of our PLC, you have up to 32 kilobytes of programs. So that means you can actually store a lot of instructions or lines of code. And then it has 8 kilobytes for data memory. So it can store information, but again, only in this very small size. So it can operate from 0 to 55 degrees Celsius. So not so high. So obviously you have to pick the PLC to use depending on the environment that you want to use it. And then this is the shape of our PLC, and it is compatible with the DIN mounting. So the DIN translates to the Deutsche Institut für Normen, which translates to the German Institute of Standardization. So it's just a standard mounting that has been agreed upon. So it's been set by the German Institute of Standardization. So let's go to the inputs. So these are the various, well, digital inputs that our PLC can receive. So for example, here, it explicitly said here that the Omron has 12 analog inputs. I believe you can still use this analog inputs as digital inputs, but it just has additional electronics that allows you to use it as analog inputs. But you can always use it as a digital input as well. So for digital inputs, so you can attach either push buttons, and then there are two types of push buttons. So it's a normally open push button. So when it's not activated, if you're not pressing it, then it's open. And when you press it, and while you're pressing it, it is shorted or closed. And then when you let go, it's now open again. You also have a normally closed version of this. So that means that when you're not pressing the push button, it is closed or shorted. But when you press it, it becomes open. And then when you let go of the push button, it closes again. So similarly, you also have switches. You have a normally open switch. When you switch a normally open switch, it shorts. And when you let go of the switch, obviously, it stays closed unless you switch it again. Now it is open again. So there's also a normally closed version of that. So you also have this the relay or contacts. So the relay now, instead of a manual operation acting on it, it is usually an electrical signal. So when there's an electrical signal that energizes your relay, so for example, a normally open relay, so by default it's going to be open if it's unenergized. So when it's energized, it becomes short. And when that energizing source continues to exist, then it remains short. And when it is unenergized, it becomes open again. So yeah, just I just explained that here earlier. So again, if you have a switch, when you press it, you have a logic high. So it's usually you usually drive it with a high. And then when you press it, you have the logic high, and so it receives a high signal. The PLC receives a high signal. And then when you let go, it becomes logic low again. Analog inputs. So again, the same here. So for the OMRUN that we showed earlier, you can have analog inputs. So for the analog inputs, it usually receives a range of voltage or current values. So say for example, you have a sensor, and then that sensor will receive some mechanical. Say for example, this one, it is a level sensor. So it could be a pressure based or mechanical, some form of mechanical based or mechanical signal is transformed into an electrical signal, say a voltage or a current, and then that is fed into our analog input interface for our PLC. So if it's voltage, it's usually typically 0 to 10 volts. If it's a current loop or a current varying signal, then it's usually 4 to 20 milliamps. So most PLC inputs have signal processing capabilities that allows it to be immune to noise when you have a current loop. So usually you have a current loop signal, a current based signal for our analog input, and then the circuitry inside of the PLC makes sure that it is immune to noise. Now let's go to the outputs. So again, similar to the digital input, you can think of these as the coils or the relay contacts. So, and usually that's how usually the outputs are implemented. The digital outputs are implemented. So it's usually in the form of a contact or a coil, which is triggered by some signal from the output, from the PLC. Again, usually in the form of electromechanical relays that are attached to actuators. So for example, as a simple operation, so you have a push button as an input. So when that push button is pressed, that turns on the relay contact that is attached to it, well, digitally stored in the PLC. So you can attach the output coil of one of the outputs and then the input push button. So you can say that whenever the push button is pressed, this coil will be turned on and then it turns on the motor. So similarly, you can also have analog outputs. So PLC will then produce say 0 to 10 volts or 4 to 20 milliamps of current. So again, here's an example of analog outputs. So for example, here you have 0 to 10 volts that is attached to a meter, and then that meter could be used to signal or to inform the operator of certain measurements that you want to measure. So this could be the pressure or the speed of your motor. It could be that. And then at the same time, the analog output again. So you have this transducer. So the coils exist here. The relay coils are usually here. And then you now have that relay coil is attached to this transducer that translate the electrical signal to some valve to some mechanical signal that controls the valve, which then controls the airflow of our air supply. So again, we have here operator interface, which has a touch screen. It has already digital push buttons and digital meters, so you can use that. But in sometimes there would also be just simple operator interfaces, which has LED indicators and physical push buttons or physical meters that are attached to it. So now, how do we actually use the PLC? Or how do we actually control the PLC so that we can tell it what to do? So there are 5 programming languages that have been published by the International Electrotechnical Commission in 1993. It is specified by the IEC 61131 specification. There are 2 graphical programming language standards and 3 textual programming standards for PLC. So the most popular one, I would say, is the ladder diagram and the instruction list. And usually the ladder diagram can be translated to an instruction list and vice versa. So here are examples of is an example of a ladder diagram. So you have here your push buttons, and then you have here, I guess this is a motor and then some overload protection. And then here's a functional block diagram, which is sort of similar to the logic gate diagrams. So the instruction list, these are some of the basic instructions. So you can think of this instruction list as a textual program. So like C, but it's much more rudimentary type of programming. So say for example, you load the variable A, you load the not of the variable A, So that's it. And then you and variable A and variable and another variable. You and the variables and not the result of those variables. So you know. So and then the output they use it as st or out. So you store the output of these operations into that signal or to that register or to that data. So that's how they interpret it. So we will have examples of how to translate the ladder diagram into instruction list later. So this is an structured text. So if you have been using C++ or some other high level programming languages, so you might be familiar with this form since it is similar to the high level programming languages. So it seems or it looks sequentially, or it forces the programmer to think sequentially, although the PLC will still run everything in parallel. So, for example, yeah, going back to the ladder diagram. So again, this network of push buttons and logic operations will be run together at the same time with this other network. And if there are additional networks of relay logic or logic diagrams, then they will actually be run at the same time, unless there are timers. So there are actually timers that delays the operation that allows for us to run operations sequentially. But again, they are technically in running in parallel. So this is the last type of programming standard, which is a sequential function chart, which looks like a flowchart. It is still technically sequential, so it also allows forces the designer or the programmer to think sequentially, but they have to remember that all of the operations run in parallel. Okay, but we will be focusing on the ladder diagram and the instruction list, so you don't really have to bother much about the other types of programming standards. Okay, so let's go to ladder programming and translating it into an instruction list. So firstly, so we have to go through the basic symbols and operations in ladder programming. So again, so you have this symbol for normally open inputs or normally closed inputs or contacts. Sometimes all the digital inputs will be symbolized by this one, even though they are a push button, a switch, they will be usually symbolized by this one. So again, if it is a contact, power flows through the contacts when they are closed. So when a normally open is true, then the contact is 1. And when the normally closed is true, then the contact is 0. Because again, when it's true or when it is high, so that means the normally closed is 0. So the coils, again, this is usually this symbolizes the outputs usually. So just to differentiate between inputs and outputs. So when you use this symbol, it means that these are digital inputs. But when you use the symbol, it means that this is a digital output. But then again, they are technically can interpret them as the same. So they are still relay contacts or activated coils. So similarly, um, if it is a normally open coil, so that means coil is energized, and if it is energized, so that means this is shorted. But there's also a normally closed coil, so that means that it will always be shorted, and if it is energized, then that means it becomes open, or this coil is set to false or low. And then boxes in the letter diagram means that these are instructions. So usually this could be timers or counters or even mathematical operations. Okay, so for example, and then what are some of the basic operations in the ladder diagram? So for example, here we have two digital inputs, A and B, and then a digital output C. And this network is called a rung. So a rung is a path between the left side and the right side of our ladder. And then this rung specifically implements the logic and operation. So that means C will be energized if both A and B are energized or shorted. If both A and B are high, because these are normally open, so if A and B are high and they're normally open, so that means they become shorted. So again, it means there is an energy or power flowing through the rung and then the coil closes. Okay, this one is an operation. So, oh yeah, by the way, this is an AND operation because the two inputs, digital inputs, are connected in series. So both of them have to be high so that the high signal will be sent to the coil. Whereas for the OR, they are connected in parallel so that only one of them needs to be high so that the coil will be energized. Either A or B needs to be shorted so that C will be energized. So you can think of an energy source occurring here, and then the power will flow from left to right. And then when there's power, then C becomes energized. Okay, the coil becomes energized. But then again, if the coil is actually normally closed, there's going to be a line here. So that means that if either A or B are high, so that means the coil is energized and now it's now open. So it basically is open. So it turns off whatever it is that C is connected to. Whatever output is connected to C, it is turned off. Okay, so the NOT operation. So you can also implement the NOT operation. So here, for example, again, if there was no bar here, so if A is shorted, then C is shorted. But here in this case, if A is by default normally closed. So that means if A is energized, then the coil is normally closed. So when A is actually energized, it becomes open. Or when you switch A, it becomes open, it becomes low. So C is then becomes energized because of that. Okay. So here's an example of a ladder logic and its equivalent instruction list. So for example, we have here two operations of our ladder. The first ladder, again, implements an AND operation. So you have input 0 and input 1. Say this could be push buttons, and then those two push buttons needs to be on so that the coil 0 will turn on or gets energized. Similarly, you have a second network here. So push button 4 and push button 5. Let's say they are push buttons. Then either push button 4 or push button 5 needs to be high or on or switch to high or to true for the coil 1 to turn high. Now, when you translate that into an instruction list, so you translate it like this. So you load push button 0, you AND that with push button 1, and then the result is going to be the, the coil 0. So the result will be stored to coil 0, so the output 0. So for example, if push button 1 is high and push button 0 is high, then coil 0, which is an output, is high. So for the network 2, which implements the OR operation, so you load the push button 4 and you load push button 5, and then you OR push button 4 with push button 5, and the result of that operation is sent to the coil 1. Okay, so that means that either push button 4 or push button 5 needs to be on so that the coil 1 will be on. So this is an example of how you would see it on the programming device. So usually the programming device allows you to input this information. And then once you're happy, you can then send that connect your programming device, your PLC, and then download that onto your PLC. And then now this instruction will be stored onto our PLC. Okay, so here's an example of a timer, or of a function, which is a timer. So again, our timer requires just, well, an input, which enables the timer, and then a preset time that indicates how long will the timer turn on. And when the timer reaches that preset time, it becomes turned off. So what happens here is when it's enabled, T on becomes high. So it produces a high. And then when it reaches that preset time, the timer turns off, and so it's now low again. So you can use this. So that's how usually timers operate. Okay, so again, so once the program has been downloaded onto the PLC and now it's operating, what it actually does is it reads the inputs first and then executes the program, all the programs in the network. So again, back to the ladder here, all the programs that if you have, say, 10 ladders, 10 instructions on the ladders, all of those instructions will be executed. Okay. And it will actually check. So if there are timers, it will check the values of the timers. And if it's not a time to turn off the timer, then it's not going to turn off the timer. But then, yeah, so it's gonna scan everything, execute the program, and then do some diagnostical communications, and then update the outputs. And then again, it will read the inputs, execute everything again. So it will just continue to do this. So that's why the PLC runs in parallel. So the PLC executes the programs in parallel. So okay, so here's an example of a motor control. So you have your input interface here so we have our three inputs. So a push button, a normally open push button, a normally closed push button, and an overload protection that is normally closed as well. So you have these networks here, and then the program that is stored in the processing unit or the CPU of our PLC. And then these are the output modules. So you have three outputs. I guess these are digital outputs. So you have the first output connected to the motor, just started, and then the second output is connected to I think this is an LED indicator that turns on when the motor is running, and you have a stop indicator that turns on when the motor is not running. Okay, so let us actually interpret what happens on the CPU. So here we have an OR operation between the push button one, which is normally open, and the coil 0. And then you have here the normally closed push button stop and the normally closed overload protection contact. So that means this is always shorted. So you can imagine that there's like a line here, normally shorted. So that means that it is high. By default, it is high. Okay. So again, when we push the push button, the IO0, so this one becomes shorted. So that means energy flows from left to right, and then our motor is energized. So that becomes energized. So that means when this becomes energized, this one, since obviously this is the output, right? But that can also be interpreted as a variable. So that means this is technically also shorted. So that means when we let go of the push button, because when you let go of the push button, it will just get depressed and become open again. So this one becomes open, but then energy from the coil is still going to be continuously energized because of this one here, because of the signal here. Okay, so now let's interpret network 2. So that means the motor, oh yeah, since this is connected to the motor, so that means it will turn on the motor. So it will now start the motor. So yeah, and unless the stop button is also pushed, so the motor will not stop. But once you press the stop button, so when you press that, this becomes open. So that means this one will now be unenergized again, and so the motor will turn off, and so this will also be unenergized. At the same time, if the overload protection detects that now say for example the current that's flowing through the motor is overloaded, so the overload protection will be energized, and that means when the overload protection is energized, it becomes open because it's normally closed, and when it becomes open, so the coil is now disconnected, so it now again turns off and this turns off, right? So for the network 2, so again, when the motor turns on, so say for example, stop was on, or the motor is on, so that means if this is on, so this variable here turns on, and so that means our coil here turns on, so that turns on the light indicator that it is running. So this could be, say, the green LED that you see. So there will be like a green LED that attached to Q01, so that is turned on. Now, if Q0 is off, so this is knotted, this is a knot. So if the Q0 is off, so this one is normally shorted, so and this one also is normally shorted, so it keeps running, so it is stopped when the motor is stopped. But when the motor is running, so that means when this one is on, so this one becomes obviously low, and so it's normally you attach not operation to here, so that means this becomes off. Okay, so it is again by default shorted, and this is by default turned on. Now when this turns on, when you start the push button, this becomes high, so it becomes the knot of this, so it becomes low, and so that's for this regular motor control. Now you can actually modify this to have an additional protection. Just say for example, this motor control is in a plant, and then you have here a limit switch. So you just modified it and then attach a limit switch here. that when it's open, the motor will not start. So it's the same network. You can see that it's the same network except for this limit switch that is attached on network 1, that is attached along here. So it is ANDed. So if the limit switch is not shorted, it will not turn on the motor. So that limit switch can be used as a safety precaution. So you can actually attach it, say, for example, here, the example is at the motor room. So if the motor room is not, if the door of the motor room is not closed, then the motor will not start. It will only start and allow you to, when you press the start button. So, for example, the motor is inside the motor room, right? And then the PLC is outside. So, if the door of the motor room is not closed, so the PLC, you cannot turn on the motor. So, even if you press the start button, it will not turn on the motor. For this final example, we have here a DC motor starter. So if you remember from the DC machines, from the machines topic, you remember that if you have, say, for example, a motor, you actually apply here current limiting resistors, right? To limit the initial current that flows to the motor. Remember, if without these current limiting resistors, initially the motor is not running, right? So it's not rotating. The rotor is not rotating. So that means that when the voltage is inserted, everything is shorted. So there's no electromotive force to counter that voltage and that current. So what would happen then is that there will be a spike, a high current that spikes and enters the motor windings. But a high current can damage the motor. So what we did in there was actually insert current limiting resistors in series to the motor windings. But we don't want those current limiting resistors to exist once the motor is actually running already. So what we do is we attach switches onto the current limiting resistor. So here, in this case, we have a three-stage current limiting resistor. So we've attached three resistors, and we run switches in parallel to them, so that we can short them out. So that the motor, there's no resistance that's adding or preventing the motor to operate in its full capacity. So to implement this, you can use the PLC. So here's an example of the ladder diagram of our DC motor starter. So say, for example, you have a start push button here. So when we short this, when we press the push button, so the run coils, so which are here, the run coils will be shorted. So when we press down here, again, this becomes shorted. And when that becomes shorted, so the run operation also becomes shorted. So you can think of that there are coils here, right? So think of these as coils. So A's are coils. Again, when the push button starts, so the run coil is shorted, so this becomes shorted. And so now current flows through and then turns on our motor. But when this is shorted, this also becomes technically shorted. So when we depress the push button, so when we depress it, so even though it's now open again, so this branch here stays shorted, which it keeps on energizing our run. So this keep on being shorted. So now when the run is shorted, so the timer one turns on. So this also turns on. And then when the timer one turns on, it will wait for 2 seconds before this contact will close. So, and after 2 seconds, it will short, and then this contact here, which is A here, will close after 2 seconds. So now this first stage of the first current limiting resistor is now shorted off. So now the current will just pass through RB and RC. And now when A is short enabled, so the timer 2 also starts. So again, shorted info. So when the timer 2 starts, so again, it will wait for 2 seconds before this one short. So when it's 2 seconds, it will now short. So again, this one though is a timer that is normally off. Normally off siya na timer. It will turn, yeah, or it will short after 2 seconds. So it's a little bit So it's a little bit different from the timer that I explained earlier. So, but yeah, again, when this timer, um, when it's now 2 seconds, when the timer has on, so this contact will close. So this becomes closed, and now current runs from, now current only flows through the RC. And then when B is closed, timer 3 turns on, and then after 2 seconds, this contact will turn close, and then when it closes, the contact C will also close. So this closes. And now the full current passes goes through the full voltage now is being observed by the motor, and now it can run at full capacity as, yeah, as said. Okay, so yeah, so that's it for the PLC. This is the end of this topic.